Hello everyone, my name is Wei Qi and today I'm going to present our work about the flexible partial MDS code. Data storage is a critical problem for non-violent memories, and the popular approach to solve this problem is that using MDS code. It means that we encode the information into a n number of storage nodes, and from any k of it, we can recover the whole messages. Nowadays, we are using SSD and it brings new challenges. Sometimes we need to face a mixed type of failures that containing the node failures and additionally symbol failures. Node failures means that the whole node is failed and we cannot access to any of the symbols, while the symbol failures means that only part of the symbols in the node is failed and we can still reach the rest of the symbols. Partial MDS code was first proposed to solve this kind of challenges. It can tolerate this mixed type of failures that containing the load failures and additionally symbol failures. However, partial MDS code is designed for a given redundancy level. That is to say, even though the number of failures is less than the failure tolerance, the rest node, we cannot make use of the rest nodes. For example, as we can see in these figures, the partial MDS code is designed for n equals to 5 and k equals to 3. So even though there is only one failure, we can still only make use of the 3 remaining available nodes and one node is wasted. In this case, each node needs to downloading all the symbols in the nodes, and thus it will result in a larger latency. In our work, we proposed a flexible partial MDS code. In this code, we can adjusting our access nodes according to the number of failures. For example, in table 1, we present a flexible partial MDS code with the number of load accessed k to be adjusted to 4 and 3 according to the number of failures. Here, k is the number of nodes we accessed, and L is the number of symbols we access in each node. In this example, the star means failures, and in this case, we have 2 node failures and 2 symbol failures. So in this case, we reach all the symbols in the remaining 3 nodes. Each node access 4 symbols, and here we can decode all the messages. Also, another case is that when we only have 1 failures, as you can see in this table, the star means failures, we only have 1 node failures and 2 additionally symbol failures. In this case, we only need to download 3 symbols in each of the nodes. It means the first 3 symbols in the remaining 4 nodes. And in this case, we can still recover the whole messages. By doing so, we can reduce the average latency. So here is an example of our performance. Assume we have 5 nodes, and each node has a failure probability of p equals to 0.1, and downloading 1 symbol takes time t. So in this case, we can use a fixed code, which k can be 4 or 3. In this case, if we need at least 4 nodes, then the probability of we successfully downloading all the messages is about 92%. And in this case, we need an average latency of 3 times t, means we only need to download 3 symbols in each node. Or we can have a fixed partial MDS code with k equals to 3. In this case, the successful probability increased to 99%. But in this case, we need to downloading 4 symbols in each node, thus resulting in a large latency of 4 times t. Or we can use our flexible partial MDS code, where the k can be adjusted to 4 or 3 according to the number of failures. So in this case, if there is at least 3 nodes available, we can downloading all the messages. So the probability of success is about 99%. And also, if we have 4 available nodes, we only need to downloading 3 symbols in the available nodes, thus resulting 3.05 times t as our average latency. In this case, you can see that we can maintain the maximum for failure tolerance, while we can also reduce the average latency. That is a brief introduction of our flexible partial MDS codes. Thanks.